This conference will now be recorded.
Hello everyone. Last day we have seen first law of thermodynamics. Okay, and also there are different statements possible for first law of thermodynamics. Now under different condition, that is whether temperature is constant, Q is constant, or P is constant, depending on that we can have different formats for first law of thermodynamics. So here we will see different cases, case 1, case 2, 3, 4, etc. Fine. After that there will be a new state function which is known as enthalpy, and there are different types of enthalpy. So once we know what is enthalpy, then there will be standard enthalpy for formation, standard enthalpy of reaction, enthalpy change during different types of phase transition, and if time permits we will also see enthalpy change in combustion process and also atomization process. So case 1, under different cases of first law of thermodynamics. So first law of thermodynamics, this is the equation for that is the mathematical expression for first law of thermodynamics. Now when it is isothermal expansion, that means del U, that will be we have to consider it as 0. Okay, now if it is 0, that means in the left hand side we have 0, so Q will be now equal to minus W. So we can also say that for isothermal processes, the heat which is absorbed by the system, that means the small q, that is actually equal to work done by the system. Now work done by the system, we have seen the sign convention in the previous class. So when it is work done by the system, it is negative. When it is work done on the system, then it is positive. So in this case you can see it is negative, so that is why it is heat absorbed by the system. Now it is equal to minus W. That means we can say it is work done by the system, which is equal to the heat absorbed. So for isothermal irreversible change, so irreversible and reversible, that also we have seen in the last class, right? So irreversible change means there will be a sudden change and pressure is fixed here, which is P external. So Q equal to minus W, that we have already seen, and we know this W is basically P into del V. Now del V means Vf minus Vi, and this P is basically P external, that is from external the pressure that we are applying. So for isothermal irreversible change, this is the formula for Q equal to minus W, and that is also equal to external pressure multiplied by del V. Del V means Vf minus Vi. Now, if it is reversible, but also isothermal, then this expression we use. And how we are reaching this expression? By integration, that we have seen in the last class. Remember? So, minus W, what we have done in that case? In that case, this term we have integrated, that is Px, that is first replaced by P internal, and then we have done the integration from the limit Vi to Vf. And after integration, the final expression we have obtained for isothermal reversible change, and that is this expression nRT ln Vf by Vi. If you remove this ln, it will be 2.303 natural log nRT log. Okay, so these are the two different expressions. This is the first case for first law of thermodynamics. So the equation is now reduced to this form. What about case 2? In case 2, it is isochoric process. That means there is no change in volume. Initial state, the value of V, volume, final state, the value of V, both are same. So no change in volume, that means work of expansion not possible. So P del V, this term as del V is 0. So obviously this will also be equal to 0. Now first law of thermodynamics, we get this equation, but you can write in place of W, you can write P del V. Now as this term is 0, that means del V will be directly equal to Q. Now we have given a subscript here for Q, which is V. So this subscript means that V is, that is del V is 0. So what we can say, during an isochoric process, the amount of heat supplied to the system, that is converted to its internal energy only, because here work of expansion not possible. So that is why del U is directly equal to Q, and this subscript means we are trying to mean here isochoric process. Case 3, adiabatic process. That means Q will be now 0. Now as there is no exchange of heat, Q is 0. So this equation now it will be reduced to del U equal to W. We are using the subscript AD. AD means adiabatic. So what we can say here, that the decrease in internal energy, that is exactly equal to the work done by the system on its surroundings. So here no question of Q because Q is 0. So whatever is the change in the internal energy, that is only because of the work done by the system. Okay. So this is 4. So in case 4, now we have considered isobaric process. That means pressure is constant. There is no change in pressure. So this equation now, in place of W, we can write P del B. Now we are not omitting any term here because here P is constant. So all the terms will be present. Now why we have put a negative sign here? Sign is not so much important because that depends on whether work is done on the system or it is work is performed by the system itself, right? So here, as there is a negative sign, so what we can say, a part of heat absorbed by the system is used for PV expansion work. That means system is doing work. So that is why there is a negative sign. If you are not putting negative sign, then it means work done on the system. And the remaining amount of heat that is added to internal energy of the system. So the part of heat absorbed by the system, it is using for two purposes. One purpose is to do some expansion type of work, that is PV work, and another one is the remaining is added to internal energy of the system. So here, as we are considering expansion work, that means work is done by the system. So that is why there is a negative sign. If it is that is, if you consider compression work, then it will that sign will be different. But whatever it is, important point is the total quantity of heat which is absorbed by the system. So in this case, as it is doing work, system is doing work. So that is why we are saying absorbed by the system. That amount of energy, some amount is, that is heat, that is used for PV type of work, and the remaining is used, or you can say added to internal energy of the system. Okay. Here we have a question. 4 liters of an ideal gas is allowed to expand isothermally into vacuum. Now this term is important here. Vacuum means here P external is 0. And we have already mentioned that when P external is 0, that means no work is possible. It is because there is no such force from external side. Okay. So that is why work is occurring under vacuum condition. So that is why work will not be there. So until, though it is saying that until the total volume is 2 liters, allowed to expand isothermally into vacuum until the total volume is 2 liters, but whatever it is, once it is mentioned that there is vacuum, then amount of heat absorbed or work done, everything will be 0. So here basically, if you consider this mathematical expression of thermodynamics, as there no work is done, okay, and also here heat absorbed, that will also be 0. Okay. Most of chemical reactions are carried out not at constant volume, that we know. Okay. So two types of conditions we have seen. One is constant volume, another one is constant pressure. But when you consider chemical reactions, that are mostly occurring under constant pressure, constant atmospheric pressure, not constant volume. So that is why this point is now becoming more important compared to the other situation where we are saying that it is constant volume. Okay. Now, as this constant pressure condition is more important when we are mainly considering the chemical reactions, that means we have to now introduce a new state function which will be suitable for this condition. Which condition? Constant atmospheric pressure. So enthalpy is such a state function which will serve this purpose, and it is denoted by capital H. At constant pressure, we know that this term we have just seen for isobaric process, this term will be changed to like this, provided it is heat absorbed by the system. So that is why there is a negative sign, because work is done by the system. So heat absorbed is QP, and minus P del V represent the expansion work which is done by the system. Now this equation you can write in different way. Suppose you are writing it for the two states. Initial state is denoted by state 1, final state denoted by state 2. So for state 1, internal energy is U1 and final state 2. Now internal energy is U2. So U2 minus U1, this difference is basically del U. So in place of del U in this equation, if you write in this way, then QP as it is, and in place of del V now we are writing V2 minus V1, where V2 is the final volume, V1 is the initial volume. Now this equation you can arrange like this. So just QP, it will be remaining as it is. Just this U2 now it is combined with PV2 and U1 is combined with PV1. So we are writing the same equation in a different way. Why we are doing so? Because now these two terms both are basically combination of U and P and V. One is for state 1, another one is for state 2. Now in place of U plus PV, we will write this new state function which is H. So how we can define this enthalpy H? It is that thermodynamic property which is defined as the sum of internal energy of a system and the product of pressure and volume. So H is basically U plus PV. So now in place of U plus PV2, you can write H2. In place of U1 plus PV1, you can write H1. Okay. So QP, now that will be equal to del H. That is difference between enthalpy. So when there is finite changes at constant pressure, we can write it in this way. Del sign we can use. But as it is constant pressure, so this del PV term, basically you can write it P del V plus V del P. But this term is 0. So that is why you are now left with P del V. So del H, now it is equal to this del U plus P del V, provided pressure is constant. So from this equation, that is the final equation, you can, what is the significance of this equation? The significance is it is reflecting, that is for del H, as if it is reflecting the capacity to do mechanical work, because P del V is a mechanical work, expansion or compression. So it is the reflecting the capacity to do mechanical work and also the capacity to release heat by the system. So both these we can understand from this equation. So that is the significance of this change in enthalpy, that is del H. Now remember here del H and Q, sometimes these two terms are, that is enthalpy and heat, both are energy, it is fine, but energy, that is when it is Q, then it is path function, but H is not path function, remember. So enthalpy and heat, these two are sometimes used for the same purpose, but there is difference, and we will also see in the next slide what is the difference. These two are obviously not same. One is state function, that is the property of the system. Another one is not a state function, it is path function. Now we have to know two new terms. One is endothermic, another one is exothermic. Now endothermic means those reactions where heat is absorbed by the system from the surroundings. That means in this case Q will be positive and del H is also positive. So if I am saying for a reaction where X is converted to Y, reactant is X, Y is product. Suppose in this case amount of energy released, that is I am writing plus, suppose I am writing 30 kilojoule per mole. So this amount of energy is released. So the released energy means it will be exothermic or evolved or liberated. And when I am writing plus and any amount of energy in the product side, that means here del H is negative. But suppose if I am writing it minus 30, that is Y, as well as minus 30. That means in this process heat is absorbed by the system. So in those cases, the process will say that it is endothermic process. Fine. So remember, when in any, suppose for any particular reaction, delage value is given as if it is minus 30 kilojoule per mole, that means this is the amount of energy released. It is the released energy. And when we are saying that it is a positive sign for delage, because for different reactions there are different delage values, and from the delage values, that is mainly from the sign plus minus, you will be able to understand whether heat is absorbed in this reaction or it is liberated in this reaction. That we can conclude from the sign of delage. Okay. At constant volume, del U, we know that it is equal to QV. So that means if it is so, this equation now it will be reduced to, now this part is 0, and we know that for isochoric process, remember we have just discussed in case 1, case 2, case 3. So there we have already seen that del U is equal to QV when it is isochoric process. So just put QV in place of del U and P del V is 0. So now we are getting del H is equal to QV. So enthalpy change, that is equal to Q, provided it is isochoric process. And then del U is also same, just like del H. Both are same, and they are also equal to QV. But this is not true for constant pressure, only for constant volume. So if we want to understand the difference between these two state functions, is not usually significant for those systems where solids and liquids are present as reactants or products. Because when it is solid and liquid, there is no such significant change in volume, right? But if you consider gas, there is significant change in volume. So when there is significant change in volume, that is you are dealing with some gaseous substances, in that case del H will be equal to not, that is directly this you cannot write, then you have to write it is del U plus P del V, because now there is significant change in del V. So this full equation we have to use. But suppose if the substances involved are solid and liquids, then volume change is not so much important. That means del V is almost 0. In that case, these two quantities will be same. So their difference is more prominent for those cases where there is significant volume change. And that is possible when you are dealing with gaseous substances. Now, when it is gaseous substances, how this equation is changing, that we will see now. So when it is reactants, suppose for initial state, from ideal gas equation, we can write this equation PVI, that is initial volume, because for final volume P is same, pressure is constant, only volume change we are considering, because now we are focusing on gaseous substances. So volume change is important, and when there is volume change, obviously the number of moles will also change. So in this ideal gas equation, P, R, T constant, V and N, these two are different with the subscript I and F. Okay. Now equation 1, equation 2, what you will do? Just subtract 1 from 2 and you will get in the left hand side P common, Vf minus Vi, or you can write P del V, and in the right hand side it is RT common, Nf minus Ni. Now this difference, that is the number of moles in the final state, that is the product side, minus the number of moles for the reactant side, that is initial state. So this difference we denote by del Ng. G subscript, it means it is gaseous substance. So that is why there is change in number of moles. Only for gaseous substances, not if we are considering the change of number of that is change in number of moles, not for solid or liquid, it is only for gaseous. That is why G subscript is used. Now this equation del H equal to del U plus P del V. This P del V, in place of P del V, now we will write del Ng RT. So this is the equation you can use when reactions, you are dealing with reactions that are involving gases. Okay. Now we will try to see enthalpy and Q, these two, how we can compare. So there is a certain difference present between them. It is true that for both we use the same unit, that is energy unit, but not all the energies are similar type. Remember, just like heat and work, though for both we are using joule or kilojoule, but they are not same. Heat is disorganized form of energy, but work is organized form of energy. Similarly, when we are comparing heat versus enthalpy, enthalpy is basically the energy which is present, and heat is basically energy which is in transit only. So suppose you are turning on a tap. So once the tap is turned on, then there will be water flowing. So this flowing water, you can compare it with heat. But once you turn off the tap, then it is true that in the pipe there is water, in the water tank there is water. So this amount of water which is already present in tank or pipe, you can compare it. It is analogous to enthalpy. So that is why I am saying energy, it is the energy which is present. But heat is energy only when there is some transition going on in transit. So when you turn on the tap, water is flowing, then only you can use the term heat. Now we will not use the term enthalpy. So sometimes we use for the same purpose, but there is difference. So enthalpy of a body is simply the net energy possessed by it at a certain point in time. So that is why it is definite. It is a property of the particular state. But Q is not property because it is only in transit. So enthalpy, net energy possessed by at a certain point in time, and it constitutes internal energy and an amount of PV work. Remember, del H is combination of del U and P del V. So this is it constituting energy, internal energy, and also an amount of PV work or mechanical work. And as long as there is no transfer of energy from that body, that is from any particular body, then you cannot use the term heat. So only when there is energy transfer between two systems, suppose because of some temperature difference, because that is also important. If temperature difference is not present, this energy transit in the form of heat is not possible. So when because of this energy difference there is transfer of energy, now you can use the term heat. Now you should not use enthalpy, and it depends on the path, how the energy is flowing from one system to another. That is through which process, because processes may be different types. So that is why it is path function, but enthalpy is not path function, though both are form of energy. For the reaction H2F2, and it is gaseous starting material, and we have another reaction which is we are getting the product hydrogen and F2. So basically here H2F2 is decomposed to two gaseous products. One is hydrogen, another one is fluorine. Both are diatomic. Now in this reaction, del U change that is given, value is already given, minus 59.6 kilojoule per mole, temperature 27. You have to find the enthalpy change for this reaction. Now enthalpy and del U, how these two are related, we know by this equation. But here it is true that del U is value is given, del H you have to find, this is given, but you do not know P del V. Nothing is mentioned about pressure or volume. So this term it will be changed by ncert, because you know the difference in number of moles gaseous substances, you also know R, and that is given, and you know T, 27 degrees centigrade. So that is why instead of using the equation del H equal to del U plus P del V, now you have to use del Ng into RT. So del H is also equal to del U plus del Ng by RT for gaseous substances when they are reacting. See, if we use this equation in place of del Ng, so you see here product side we have 1 mole, and reactant side we have only 1. So del Ng value should be 2 minus 1, 1. 27 you have to convert it to Kelvin, so it will be 27 plus 273. Now put all these values, that is the value of del Ng, value of R, T, and del U is already given, but be careful about the unit also. Here it is in kilojoule. So here del U value is given 59.6, and we will have to be very careful about the units, because when this is in kilojoule, final answer it is asking also in kilojoule, so it is fine, but you have to be careful whether the unit of this part is in kilojoule or not, because when you are putting the value of del Ng, you are putting the value of R, which is in joule. You are putting temperature, so this joule you have to convert to kilojoule, so that is why 1000, it is divided by 1000. Okay, and finally we are getting the answer after putting all these values, del U, del Ng, RT, we are getting minus 57.1. Nearest integer will be 57, and there is negative sign already present, so it is an integer type of problem. Final answer is simply 57. We don't have to consider the negative sign, it is already given in the question. Fine. Now once we know enthalpy, now there are different types of enthalpy possible depending on what type of reaction you are doing. Different reaction, different types of terms for enthalpy we will use. The first we are going to use is standard enthalpy of formation. So what is the definition? Standard, suppose I am saying standard enthalpy of formation for carbon dioxide is X, kilojoule per mole or joule per mole, whatever. So what it means, what I am trying to mean by this statement, that standard enthalpy of formation of CO2 is X. What I am trying to say? It is the change in enthalpy that takes place when 1 mole of a compound. So when I am saying for CO2, that means when 1 mole of CO2 is formed from its elements present in their standard state. So as I have taken the example of CO2, and CO2, what are the elements present? Carbon and oxygen. So carbon and oxygen, these two are present. Fine. Now we know under normal condition it is gas. And what it is constituent? Constituent is carbon, first element, second element is oxygen. Now try to understand. The element from which you are making CO2, what are their standard state? Under normal condition, carbon is solid, it remains in solid form. Under normal condition, oxygen is diatomic gaseous molecule. So now you have to consider it like this. Carbon, solid state. Oxygen you have to write in the form of O2, because that is the under normal condition. Normal condition standard state means 298 Kelvin, room temperature and 1 bar pressure. So when you are maintaining this condition for its elements from which CO2 is produced, and also it is only for the 1 mole of the substance. See, if I am saying it is for CO2, it is only for 1 mole of CO2 you have to consider. So in this reaction, the enthalpy change that you will get, you can say that is the standard enthalpy of formation for CO2. And by convention, the standard heat of formation of all the elements, it is assigned a value of 0. That is the convention. That is only for elements, it will be 0. So here we have example. We have taken methane. Methane under normal condition is gaseous. So here it is written in the bracket gaseous. Now constituent elements, carbon and hydrogen. So in methane there is 1 carbon, 4 hydrogen. So for 4 hydrogen you have to take 2 H2, gaseous, and carbon we are considering the graphite form, and it is solid. So in this case it is that is standard enthalpy of formation. It is written in this way. Subscript we are using F, which means F means F for formation, and this sign is not sign is because its significance is we are trying to understand it is standard condition. So that is the significance of this dot sign. So this standard enthalpy of formation, the value we are getting minus 74.6 kilojoule. Similarly, another compound we have taken standard enthalpy of formation for ammonia, and it is for ammonia formation 3 hydrogen atoms required. So what you will do? You have to write H2. You cannot write 3H because under normal condition, it is diatomic. So you have to write it in the form of H2. But coefficient you can write in such a way so that total number of hydrogen atoms becomes 3. So that we have written 3 by 2 H2. And for nitrogen, we just need 1 nitrogen atom. So we have written half coefficient and it is diatomic. So N2. So half N2 means only 1 nitrogen atom. So this is the value of standard enthalpy of formation for ammonia, which is minus 46.0. Next, we have to understand what is standard enthalpy of reaction, another term. Standard enthalpy of reaction. Now, we will be considering any reaction and the corresponding change in enthalpy. So, standard enthalpy of reaction is a change in enthalpy for a reaction, any reaction, when all the reactants are products, they are under in standard state. So again, you have to maintain this condition, then only you can use this definition. So standard enthalpy of reaction, it is how you will calculate it when you will be actually, suppose you have any reaction and you have to find standard enthalpy of reaction for that particular reaction. So how you will do so? It is actually equal to the difference between standard enthalpy of formation of product. So what you will do, you will take summation of all the del HF dot values for all the products. So here we have taken this equation. Product side you have C moles of capital C, D moles of capital D. So these two are products. So what you will do, in place of summation del HF naught, you will put coefficient multiplied by the enthalpy of formation for the compound C. Then coefficient D for the another product, capital D. So you will put del HF naught value. So del H naught value we have just seen. That is a previous discussion. So you will put these two values. We have to put this coefficient. Otherwise it will not be correct. Then minus summation of whatever substance we have present. If it is only 1, then 1. If it is 2, in this case it is 2, A and B. If it is 3, you have to put all the 3 separate enthalpy values. And don't forget the coefficient. So coefficient multiplied by enthalpy of formation for the reactant A and B multiplied by enthalpy of formation for the another reactant, which is B. So you have to put these 4 values. And finally, after calculation, you will be able to know the enthalpy of reaction for this reaction, that is AA plus BB equal to CC plus DD. We have taken a general reaction so that you can get the clarity how to do the calculation. But it may vary, that is product side it may be more than 2 substance or less than 2, and also for the reactant side, right? So once we solve problem, you will be getting more clarity. Here enthalpy of formation values for these 4 compounds given. What are the 4 compounds? Here we have compounds CCl4. So for CCl4, the value given minus 105. We have water for which the value 242 given. So all these physical state that are mentioned in the bracket, these are very important, because whether you are considering is, suppose just take water, whether you are considering the liquid form or gaseous form, depending on that enthalpy may be different. So you have to be careful about the G, this whatever is mentioned, that is a physical state, that also important. CO2, the value is given minus 394 and other product minus 92. So these two are basically product, these two are reactant, because look at the reaction. CCl4 with 2 moles of water, it is producing 1 mole of carbon dioxide and 4 moles of HCl. So from this individual enthalpy of formation values for the 2 reactants, CCl4 water and the 2 products, CO2 and HCl, we will use all these 4 values. We will put in this previous equation, I mean to say this equation, and then you will be able to get the answer. Okay. So summation of enthalpy of formation of product. It will be minus 105 and 2 into minus 242 because there is coefficient 2. Then minus, simply put minus 394 and 4 HCl, that means 4 into minus 92. So enthalpy for this reaction, this part we are getting from product side and this part we are getting from reactant side. If you are taking bracket here, you can put positive sign here. So from the product side, it is minus 394 multiplied by minus into 4, this quantity, and then this negative will be cancelled because for CCl4 the value is negative, this is also negative, right? So negative and there is a negative sign, so ultimately it will be positive. So 105, that is for CCl4, it is only 1 mole, there is no coefficient you have to multiply, but for water you have to multiply 2 with 242. So once you are done, you will be getting this final value minus 173 kilojoule per mole. And also be careful whether these individual values of enthalpy of formation, whether the unit is kilojoule per mole or not. Because suppose if it is given in joule, for two substances it is given in joule, for other two it is given in kilojoule. So you just have to check whether all are in same unit or not. Then only you can put in this equation. So this is the final value. Enthalpy of reaction for this magnitude of enthalpy of reaction in kilojoule per mole. So this is the value. Another problem. At 25 degrees centigrade, enthalpy of the following processes are given. So 4 different reactions are given, corresponding del H naught values, standard enthalpy values are given for each of these 4 reactions. So total 4 reactions, total 4 enthalpy values, all are standard condition. You have to find what would be the value of X for the following reaction. X means enthalpy change for this reaction. Now suppose this is reaction number 1, this is 2, this is 3, and this is 4. Okay, and this is a new equation, suppose this is 5. So you have to find the enthalpy change for the last equation, that is equation number 5. But you are having the information for enthalpy values for these 4 equations. So what you will do, whenever you will get this type of problem, the first thing that you have to do is arrange these 4 equations. It is not necessary you have to use all the reactions given. There may be some extra information or extra equation in the question, but it is not mandatory you have to use all the equations. Your purpose is to arrange the equations given. You can take 2 equations, you can take 3 equations, or you can take all the equations. But you have to arrange them in such a way so that you can get this equation. So you can add the equation, you can subtract the equation, you can add coefficient in both left hand side, right hand side, or you can divide with some, that is fraction coefficient is also fine. That is you are multiplying half both sides. That also you can do. But ultimately you have to arrange the equations in such a way so that you can get the final equation. Now depending on how you are arranging this, suppose you are simply adding equation 1 and 2 and you are getting equation 5. In this case it is not, I am just saying simply. So for this third equation that you are getting simply by summing the 2 equation 1 and 2. So for the third equation the enthalpy change will be the summation of the enthalpy change for the first equation. Because it is state function, so you can simply add or subtract the del H values. So here we will try to arrange these 4 equations in such a way so that we can get this equation. So see here left hand side we have water molecule gaseous. Water molecule gaseous you can see here. Okay. And in the right hand side we have H gaseous, HO gaseous, negative, positive, nothing is given. Now we have HO gaseous here and we have H gaseous here. We don't need this half oxygen because O2 term is not involved. We also don't need O. So equation 4 is basically not required. Now, as 2HO, that is present in the right hand side for equation 1, and for the desert, that is the final equation that you have to, for which you will find del H, there also it is on the right hand side, but it is single HO, here it is 2HO. So what we will do, equation 1 multiplied by half both sides. Once you do, what you will get? You will get half H2 gaseous. I am not writing for simplicity. You will get half O2. In the right hand side, you will get HO. Okay. Now the next equation, we have H2O on the right hand side, but we need it in the left hand side in the final equation. So what we will do? We will subtract equation 2. So it will be H2 negative half O2 negative H2OG. So this is equation 2 with half sign. And the third equation, H2G. Now H2G, we have to cancel this because in the final equation we do not have any H2 term. So that is why what we will do, H2G, again we will multiply with half. So equation 2, 3 multiplied by half. So if we do so, it will be half H2, and this side, that is product side, we have 2H. So half, if you multiply, it will be H. Okay. So now if we finally do the calculation, here H half H2 half H2, that means total 1 H2, that will be cancelled. This term you can bring in the left hand side, and these two cancelled. These two are already in the left hand side, right hand side. So finally you are getting equation number 5. So equation 5, how you are getting? You have multiplied equation 1 and 3 with half, then you have added it and you have subtracted equation 2. So what we have done, 1 and 3, these two equations multiplied by half, then subtract, we have subtracted equation 2. So see, for equation 1 the value is 78, for 3 it is 436. So we have written these two values with the half, and for the second equation it is minus 242. So minus minus will be positive, it will be ultimately 242. So X value is positive 499 kilojoule per mole. This is the final answer, nearest integer. So it will take some time because we have to arrange the equation, and here you can also see this equation is totally redundant. It is extra information. We have not used it. So it is not necessary you have to use all. You just have to arrange all the equations, and how you are arranging, depending on that, you just have to follow. That is how you have arranged. Accordingly, you will put the enthalpy values for the equation. So if you have subtracted it, you also have to put negative sign. If you have multiplied with some coefficient, here it is half, it may be some whole number also. So you just have to multiply it with the enthalpy values, corresponding enthalpy values. Enthalpy change during different types of phase transition. Now phase transition means what? Suppose from solid you are moving to liquid state, or from liquid state you are moving to melting, that is solids, liquid to solid, fine, freezing. So melting, freezing, it may be vaporization, it may be vaporization means liquid to gaseous, it may be sublimation also. So sublimation is from solid state to liquid state. So phase transitions like this, melting, freezing, vaporization, sublimation, they occur constant temperature and constant pressure. So constant pressure, now del H term is important because we know it is important for different types of reactions where temperature is constant. It is also important for phase transition. So these are not chemical reaction, but it is physical change. But there is also temperature pressure constant. So that is why enthalpy change is important. So now we will see enthalpy changes during different types of phase transition. First is vaporization process. Actually, there may be different types of phase transition. I will not discuss all of them. Just see, if I am saying this, that vaporization, this is the enthalpy change. The same thing you can also apply for any other phase transition. Okay. So we will just see melting and vaporization, these two processes. You can also apply the similar concept. You can also apply for sublimation. That is other phase transition. So for vaporization, obviously there will be some enthalpy change. Enthalpy change involved in the vaporization, but it is not just for any quantity. Quantity is fixed. Temperature, pressure, there are some fixed values. See, when you can maintain all this, then only you can use the term standard enthalpy. Suppose you are not maintaining this pressure, then we cannot set a standard enthalpy of vaporization. Okay. The standard sign, we have used this not. The enthalpy change involved in the vaporization of 1 mole of liquid, and this 1 mole quantity is also important. At constant temperature under standard pressure is called standard enthalpy of vaporization. It is also called molar enthalpy of vaporization because it is only for 1 mole. So we will denote it del H VAP subscript, which means vaporization, and not sign is there, which means standard state. So standard enthalpy of vaporization, just take this example of water, very simple. From liquid state, now it is converted to gaseous state, and in this process, see, this is a positive sign. That means it is endothermic process. Here heat will be absorbed, and that is understood because once you apply heat, the liquid will absorb that heat, then only it can be converted to gaseous state. So we cannot expect it to be exothermic. It has to be endothermic. So positive sign. So this amount of energy will be absorbed. Next process we will see fusion. So vaporization, fusion, that is basically melting. So enthalpy change involved in the melting of 1 mole of solid substances, again in standard state. So what is standard state? That is already mentioned. It is not written in detail. That is called standard enthalpy of fusion or molar enthalpy of fusion because it is only for 1 mole. So subscript we have used FUS, which means fusion, and this is also endothermic because when you are changing from solid substance from solid to liquid, obviously it will absorb heat. Fine. So all the enthalpy of fusion, it will be positive. Standard enthalpy of fusion is given for ice, which is 6 kilojoule per mole. Okay. So here we have seen two enthalpy changes. One is for vaporization process, another one is for fusion or melting process. Similarly, you can also use the same type of definition when it is sublimation process. That is direct, the phase is changed from solid to liquid state. Standard enthalpy of combustion. So combustion is a special type of reaction where we use oxygen, and if that is oxygen, it is reacting with the substance. Mostly it is hydrocarbon we talk about. And there is, when it is hydrocarbon which is basically containing two elements, carbon and hydrogen. So carbon and hydrogen reacting with oxygen, carbon will produce CO2, hydrogen will produce water. But not necessarily it has to be hydrocarbon always, it may be any other substance also. So standard enthalpy of combustion is the enthalpy change involved when 1 mole of a compound is completely burnt in oxygen. So oxygen must be present as reactant in the left hand side, otherwise it is not combustion. But don't think that mere presence of oxygen you will don't consider it as combustion. It is only there is specific condition for combustion. So any substance reacting with oxygen, we cannot say it is combustion. Okay. So enthalpy change involved when 1 mole of a compound completely burnt in oxygen under standard condition, then we can say that this is standard enthalpy of combustion. Now these are exothermic in nature. Here we have different types of substances. See, we have taken carbon. So when it is carbon, it is simply CO2. When it is a hydrogen, it is H2O. We have taken a metal. We have taken When it is metal, it is MgO, and when it is carbon monoxide, which is oxide of carbon, then we are getting again CO2. You can also say this is an oxidation type of reaction. And then we have CH4. Now this is hydrocarbon. These two examples are hydrocarbon, only carbon hydrogen present. And balancing these equations for hydrocarbon, it is very easy, because mainly in problem related to combustion that you will get, you will see mainly hydrocarbons are present. So balancing will be required, that will be required when we will solve problems, and that is also easy to do. So first you just have to write CO2 and H2. Now, as in CH4 there is 1 carbon and 4 hydrogen. So obviously to balance hydrogen you have to put 2 H2O. To balance carbon, no coefficient required, it is okay. Now once you have fix this coefficient in the product side, now try to see how many oxygen atoms are present. So in CO2 there are 2 oxygen atoms, in water 2 molecules of water, total 2 oxygen atoms. So total 4 oxygen atoms should be present in the left hand side. So that is why the coefficient we are using 2. Similarly, when it is acetylene, 2 carbons, so you have to put 2 coefficient before CO2, 2 hydrogen, so simply H2 is fine. Now total number of oxygen here 4, total number of oxygen here is 1. So 4 plus 1, it is 5. So now the coefficient is 5 by 2, because 2 will be cancelled, and you will be left with only 5 oxygen left hand side as well as right hand side. Then we have ethanol, and here we are getting again the same compound, that is CO2 and H2. So when it is hydrocarbon, product side you will get carbon dioxide and water. And look at all the values. Kilojoule per mole unit, 25 degrees centigrade. All these values negative. That means it is exothermic process. 28 liter of carbon dioxide is produced on complete combustion of 16.8 liter gaseous mixture of ethene. Ethene means H2C double bond CH2. Ethylene or ethene. Formula is C2H4. And we have also methane. Total volume is 16.8. We do not know the individual volume. Total volume is given. And from this total volume, after combustion, this is the amount of CO2 we are getting. So this 28 liter CO2, basically you are getting it from both of these hydrocarbon. This is the total amount of CO2, because CO2 will be generated in both cases. Conditions given, heat evolved during the combustion process, that we have to find. Some informations are given. What information given? Individual heat of combustion, that is CH4 minus 900 kilojoule, and heat of combustion, you can put the subscript C here also, it doesn't matter. That value is also given. So from this information, final volume of CO2 given, initial volume of 2 reactants, hydrocarbon reactants, that also given. From this we have to find the heat evolved during the combustion process. First step we will do, we will write the equation for combustion. We will write the balanced equation. How C2H4 reacting with O2, how methane is reacting with O2. So volume of ethene, that is ethylene, we will consider as X. So this is the first reaction for ethylene or ethene. Initial volume C2H4X, and this is gaseous. Here oxygen will be completely burnt, so after reaction it will not be present in the medium, and after reaction C2H4 will also be consumed. So in the finals, once the reaction is over, you will have only one gaseous substance, because this is liquid. You will have only one gaseous substance, which is CO2. So from one volume of A, that is, suppose if I am saying it is 1 volume, it is 2 volume. So as it is X volume, it will be 2X volume. Because for gaseous substance, this type of coefficient you can directly correlate it with volume. So from X liter, you are getting 2X liter of carbon dioxide. Same thing also do for methane. Because in the, that is balanced equation, first you have to write the balanced equation. I have already told you how to balance it. So if the total volume is 16.8 for these two, obviously you have to now write 16.8 minus x, that is the amount of volume for methane. After reaction, only one gaseous substance present. So here from 1 mole of CH4 you are getting 1 mole of CO2. So that is why this is also 16.8 minus x. So if this is liter, obviously the same amount in liter will be produced in the product side. Once we know this, next we will do total volume of CO2. We know it is given 28. So 2x is the amount of CO2 you are getting from ethylene, and 16.8 minus x, that ethylene you are getting, sorry, that CO2 you are getting from CH4. So if you add these two, that is equal to 28. So from this equation you can get the value of x, which is 11.2 liter. Now as these values are kilojoule per mole, that means if you know the number of moles of ethylene, if you know the number of moles of methane, suppose it is A moles, this is B moles. So B into 1400 minus and A into minus 900. If you add these two, that is actually your answer. So next step, you have to find the number of moles for these two hydrocarbon, two starting material, C2H4 and CH4. How you will do so? You will simply use the equation PV equal to nRT. That is ideal gas equation. From PV equal to nRT, first we will try to find out the number of moles of methane. PV equal to nRT means N is equal to PV by RT. Pressure is given 1 bar, which is almost equal to, sorry, 1 atm. So it is fine. Directly atm is given. Volume is 5.6. Now where from you are getting so? It is basically 16.8 minus 11.2, because that is the volume of this amount. That is the volume of methane. So put it here. R is, you have to use the liter atmosphere unit. No, don't use 8.314 because now volume is in liter, and temperature 298, 25 degrees centigrade. So from this you are getting the number of moles of methane, 229. So similar way just follow for ethylene also. So for ethylene, pressure same. V, it is directly this value. This is 16.8 minus x, but here directly it is x. These are again same. So it is basically just a double amount, 0.458. So finally the answer will be, with 229 moles, we will multiply it with minus 900, and with this we will multiply minus 400. So minus sign, if you do not consider, it doesn't matter, because ultimately it is asking the heat evolved. So simply from these two, the numerical value that you are getting, it depends on the format of question. If negative sign is given here, you will put only the positive. But heat evolved during the reaction, already it is saying evolved, so minus sign here not used. 847.3 kilojoule. That is the total amount of heat evolved. Fine. So we will end the session here. We are at the end of the session. Thank you for listening.